Hi, in this video we are going to talk about remaining bitwise operators. Let us talk about the first operator, which is left shift operator. What this operator does, it takes two things as a parameter: a number whose binary representation to be shifted and another number that tells you how many times it needs to be shifted. So the first number here, it represents the number whose binary representation is to be shifted. The second number here represents how many times this binary representation to be shifted. Let's take x equal to 3 as an example. So this is the binary representation of x, 3, right? Last two bits are set, 1 and 2, they mean 3. When you left shift it by 1, what happens is these 31 bits, since we are shifting it by 1, and I'm assuming here that numbers are represented using 32 bits, please note that your integer might be represented using 64-bit or 16 bits also. Here I'm assuming 32 bits. So these 31 bits will move to the left side, right? They will come here. So these are moved this way. And this bit is ignored. Whatever value it has, it's not considered, right? It's ignored. And a 0 is added at the end. This is added at the end. Right? Since we have shifted by 1, so 1 0 is added at the end. If you shifted by 2, then 2 zeros will be added by the end. And 2 leading bits will be ignored. If you shifted by I, then I zeros will be added at the end and leading I bits will be ignored. So you can say shifting by 0 does not make any change, right? Because you're shifting by 0, right? So shifting by 0 does not make any change. Shifting by 1 shifts the bits by 1 position and put a trailing 0. Shifting by 2 shifts the bits by 2 and puts a 2 trailing zeros. So what is the decimal value of this number that we got after shifting by 1? It's 2 plus 4, 6. So the first line of output in this program is 6. This line produces 6. Let us now talk about shifting by 2. So when you shift this number by 2, these last 30 bits, they are moved to position back. And you add new trailing zeros. So whatever values these bits have, they are ignored. They are simply ignored and removed. And 2 new bits are added at the end. So what is the decimal equivalent of this number? It's 1, 2, 4, 8. 8 plus 4, 12. So the next output is 12, the result of shifting by 2. Let us now see shifting by 4. We have a variable y and we are shifting x by y and y's value is 4. And we're storing this result in another integer z. So what is the value of z? We take the last 28 bits, considering the 32-bit binary representation, shift these bits to the left side, ignore these 4 bits, these 4 leading bits, right, and add 4 zeros at the end, 4 0 bits at the end. So what is the decimal equivalent of this number? It's 1, 2, 4, 8, 16 and 32. 16 plus 32 is 48. So the last line of output, the Cout Z, it prints 48 on the screen. So that's the output of this program. One interesting property to note about left shift operator is, if we take a closer look at this left shift operator, we can notice one property. X left shift y is equivalent to x into 2 raised to the power y. Assuming that first y bits in binary representation of x are zeros. Because if they are ones, then you are actually going to reduce the value, not going to multiply it with some value, right? So let's see this property with these examples. X left shift 1, what is it equivalent to? 6. And you can say it's equivalent to 3 into 2 raised to the power 1. X was 3 and this value was 1. So 3 into 2 raised to the power 1. X left shift 2, this is equivalent to 3 into 2 raised to the power 2. X is 3 and y is 2, right? X is 3 again and y is 4. And we got 48, which is 3 into 2 raised to the power 4. Because y was 4. So this expression can be used to multiply with a power of 2 when your input has small value. Let us now talk about right shift operator. Right shift operator is opposite of left shift. If you right shift a number x by 1, all the bits in binary representation of x are shifted toward right one position, and the last bit is ignored, and one leading 0 is added at the beginning. Let's see with this example. We have x equal to 33. This is binary representation of 33. 1, 2, 4, 8, 16, 32, 32 and 1, 33. Now when you right shift it by 1, what happens is this last bit is ignored, it goes away. And if you consider 32-bit binary representation, then there are 31 remaining bits. These 31 bits move one position right, they come here. And a 0 is added at the beginning, right? So that's what happens when you right shift this x by 1. This is the value of x right shift 1. What is the decimal equivalent of this? Decimal equivalent is 1, 2, 4, 8, 16. So the first line of output for this program is 16. Now what is the value of x right shift 2? When you right shift by 2, the last 2 bits are ignored. They are removed. And remaining 30 bits, if we are considering 32-bit binary representation, then these remaining 30 bits are moved 2 positions toward their right. And 2 zeros are added at the beginning. That's what happens when you do a right shift by 2. Last 2 bits ignored, remaining bits moved to 2 positions toward their right, and 2 leading zeros added. So what is the decimal equivalent of this? 1, 2, 4, 8. So this line prints 8 as an output of. Let us now talk about right shifting by 4. Here I have a variable y equal to 4 and we are now shifting x by 4. When you right shift it by 4, the last 4 bits are ignored. Does not matter what is their value, your output does not depend upon the value of the last 4 bits. The remaining 28 bits, if we are considering 32-bit representation, are moved toward their right. And 4 zeros are added at the beginning. Right, so there is a 0 here, and this is a binary representation. These are 28 bits if 32 bits are considered, and these are 4 leading zeros and added at the beginning. Now what is the decimal equivalent of this? These are all zeros and the value of this is 2. So the output of this third line is 2. If we take a closer look at right shift operator, we can notice that x right shift y is equivalent to dividing x by 2 raised to the power y and then taking the floor of this value. Let us take a look at this example. 33 right shift 1 is equivalent to 33 divided by 2 raised to the power 1 floor. What is the value of it? 33 divided by 2 is 16.5, and if we take the floor, we get 16. That is what we have here. X right shift by 2. 33 divided by 2 raised to the power 2. 33 divided by 4 is 8 point something, whose floor is 8. X right shift y. 33 divided by 2 raised to the power 4. Y is 4. What is the value of it? 2 raised to the power 4 is 16. 33 divided by 16 is 2.5. And floor of this is 2. So you can see this formula is valid for all this example, and this works. If you want to divide a number by 2, you can use a right shift operator. So you can notice that this formula is valid for this example. In fact, we can use right shift operator whenever we want division by a power of 2 with floor value. We can always use the right shift operator. Let us now talk about the last bitwise operator. It's a NOT operator. It does invert all the bits in binary representation of a number. It's a unary operator. It takes a number, considers its binary representation, and inverts all the bits in the binary representation. And whatever decimal equivalent of this modified binary representation is, that number is returned. Let's see this example. Say you pass x equal to 1, right? This particular operator is tilde operator. In your keyboard, there is a button below the escape button. It's there. You can press it to get this operator typed. So when you do negation of x or not of x, all the bits are inverted. This 1 becomes 0 and all these zeros, they become 1. And decimal equivalent of this number is returned. Please note that I have used unsigned int x here. I'll talk about what happens when you use signed numbers, but let's first consider unsigned int x equal to 1. So when we say unsigned, it means all the numbers represented by this data type are 0 or positives. No negatives allowed. And the range of these numbers depend upon the size of unsigned int type. Most popular size is 32-bit. So if you consider 32-bit representation, then these unsigned data types have range from 000 to all ones. Right? So these are 32 zeros and these are 32 ones. So what is the value of this number? This is 0. And what is the value of this number when you have 32 ones? What is the value of a number when you have 3 ones? It's 2 raised to the power 3 minus 1. When you have 4 ones, it's 2 raised to the power 4 minus 1, 15. So this number has value 2 raised to the power 32 minus 1. So this is the minimum value you can represent using 32-bit unsigned numbers, and this is the maximum value you can represent. So this is the maximum value we have when we have all ones, and this is the minimum value we have when we have all zeros in unsigned numbers. So this is the largest number that you can represent in 32-bit unsigned integers. This number is going to have all ones in binary representation. Please remember, how did I get this number? If you store unsigned in 3 bits, then when will you have maximum value? When all these 3 bits are 1. And what is the value of this? This is 2 raised to the power 3 minus 1, 7. Right? Considering that you have a very limited compiler and you have only 3 bits to represent unsigned integers. Similarly, if you have 4 bits, then your maximum value is going to be all 4s, which is 2 raised to the power 4 minus 1, which is 15. In general, we can say when we have n bits to represent unsigned integers, then our maximum value is going to be 2 raised to the power n minus 1. So if n is 32, then this is the maximum value we can represent using unsigned integers. This is the maximum value we have. And binary representation of this number is all ones, all 32 ones. Now can you guess the output of this program? When you toggle all the bits, you get a number which has first 31 bits as 1 and last bit as 0. And this number has all 32 bits as 1. So the number that you are going to get as an output is 1 less than this number. So your output is going to be 1 less than this number, 4294967294. That's the number you will get as an output when you do negation of x and when x is 1. Now can you pause this video and try to guess the output for this one? The output of this line is this number where you have all ones minus 5 because you have 2 zeros in this number which correspond to decimal value 5. So basically you have subtracted 5 from this number, and that's what you get as an output when you print the negation of 5. Let us now talk about signed input, and it's trickier, so you need to be attentive in this video. When you talk about signed numbers, signed integers in particular, they use a sign bit, a special bit, the leading bit, which represents the side. So when I say leading bit, I mean this bit. If this bit is 0, then this number is a positive number. And if this bit is 1, that means it's a negative number. So if you do negation, bitwise negation of a positive number, and if your number is signed, you are definitely going to get a negative number. because this bit 1 means it's a negative number. Also, signed bits are typically represented in 2's complement forms. So this is how the representation goes for signed numbers. If the number is positive, simply do decimal to binary conversion, have the first bit as 0 and write the number as it is. So binary equivalent of decimal number 1 is simply do usual decimal to binary conversion. Whatever you number get, you put it in 31 bits and you put a 0 before it, right? For example, 5 here, its binary equivalent is this and a 0 at the leading bit. So you have 31 bits to represent positive numbers. Similarly, you have 31 bits to represent negative numbers. So the range of numbers that we have in case of signed numbers, here I am assuming that we have 32 bits to represent the signed numbers. If you have 64 bits, then all the things change accordingly. It becomes 63 in place of 31, right? And that becomes 32 or 64. This also becomes 64. This also becomes 64, right? So in case of 32 bits, your range of signed numbers is minus 2 raised to the power 31 to 2 raised to the power 31 minus 1. That's the range you have. That's the possible values that you can have. So this number is represented by first 0 and then 31 ones. And this number is represented by 1 followed by 31 zeros. Now, in case you are wondering why zeros, let's talk about 2's complement representation. Signed numbers, when they are negative, they are stored using 2's complement representation. So the simple rule is, if the number is positive, put a 0 and put the binary representation. If the number is negative, put a 1 and then put 2's complement representation in remaining 31 bits. Why are we using 2's complement representation? You can read the details in computer architecture. You must have studied there. The main reason is not to have two representations of 0. Imagine a situation where you were using simply one sign bit and then using simply decimal to binary conversion. If that happens, then you will have two representations of 0, one positive 0 and one negative 0. And the disadvantage of this is your range reduces by 1 and 0's representation becomes confusing. So that is why we use 2's representation. It allows us to have bigger range and has only one representation of 0. So what is 2's complement representation? If you have a number x in n bit representation, then its 2's complement is 2 raised to the power n minus x. So if you consider a 3-bit representation, just to simplify the example, say you don't have 32 bits to represent a signed number, you have only 3 bits. Let's do this example. So n is 3. How will you represent minus 2? You will represent its binary as 2 raised to the power 3 minus 2, right? So this is 8 minus 2, which is 6. And what is the binary representation of 6? It's 1, 1, 0. So 2's complement representation of a number minus 2 in 3 bits is 1, 1, 0. If you apply the same analogy here, can you figure out what number is represented by this? What is this number? It has 31 ones and then a 0. So this is having decimal equivalent as 2 raised to the power 32 minus 1 minus 1, right? Because all ones means 2 raised to the power 32 minus 1, right? That's what all ones mean. When you have all ones but last 0, you have 2 raised to the power 32 minus 1 minus 1. So if you apply this analogy, what is the value of x, whose binary representation is this? The value of x is 2 raised to the power 32 minus 2. So value of x is 2. This is actually 2 raised to the power 32 minus 2. So if you have signed numbers and if your computer uses 2's complement representation for signed numbers, then the output of this program is going to be minus 2. Right, this part minus 2. Because this is what you get when you apply the negation operator. And once you apply the negation operator, your last bit becomes 0 and you have the decimal equivalent of this number as this by simply following this. This is the decimal this is binary representation of 2 raised to the power 32 minus 1. So this is 2 raised to the power 32 minus 1 minus 1. We are simply subtracting 1 from it to get this number. And which is 2 raised to the power 32 minus 2. Since it is 2's complement representation, why are we considering 2's complementation? Because this has to be a negative number, because the first bit is set. So whenever you have the first bit or leading bit as set, you need to consider the 2's complement representation. And which number has this 2's complement representation? If we apply this analogy, we get that number as minus 2. If the value of your number x is 2, then your 2's complement representation is this, 2 raised to the power 32 minus 2, because n is 32 and this has to be x. So that is why you get the output as minus 2. Now if you print the value of this, can you guess? Can you pause this video and try to guess the output for this one? What will you get here? We'll get 2 raised to the power 32 minus 1 minus 5. Basically, we have subtracted 5 from this number, right? These two zeros. These two ones here, they become zeros here. So what is this value? This is 2 raised to the power 32 minus 6. So what is x here? X is 6. So this is 2's complement representation of minus 6. So you will get the next output as minus 6. In this video, we talked about left shift, right shift, and negation operators. Negation is really tricky because it changes all the bits, converts positives to negatives if you have signed numbers. And please note that C++ standard does not mention anything about 2's complement representation. Your computer or your compiler is free to choose any representation for negative numbers. So output of this program might be compiler dependent. Similarly, if you apply left shift and right shift operators for negative numbers, your output is undefined by the standard, and it's generally not recommended to use left shift and right shift operators for negative numbers. Similarly, if you apply left shift and right shift operators for negative numbers, the behavior is undefined according to C++ standard. So it's not recommended to use left shift, right shift operators for negative numbers. In fact, it's not recommended to use tilde operator or negation on negative numbers, because standard does not say anything about internal representation and you may get unexpected results.